Most advanced mechanical moles can dig 2 feet every hour. At that rate, tunneling 24 hours a day, it would take 1,000 years to reach the center. We'd have to make them work faster, much faster.
And if you think of the tunneling machine as a very large beer can, and it's travelling end on end down through the earth with cutters up front, the closed face, it means that the cutters cutting away at the soft ground are separated by a wall from the men on the inside, and all of the spoil, all of the earth that's being cut is carried to the surface in pipes.
The amount of rock and spoil coming out of the tunnel is almost unimaginable. We'd need to extract 4 giant truckloads of earth per hour, 100 per day, 36 million truckloads in all. And that's if we tunneled straight down, not on a grade. We'd have to design a new type of vehicle to transport us through the tunnel. Maybe a capsule able to withstand the extremes found deep inside the earth.
The deeper we go, for every kilometre in depth, we're picking up a 30 degrees centigrade temperature rise, and that is causing us problems. The rock is getting softer, it's getting ductile as a result of the higher temperatures. We're having to resist those temperatures so that people can work within the tunnelling machine, or we would need to produce a remote machine. I think we're now stretching credibility.
But it's not only temperature that will be a problem. There's also massive pressure down there.
Yeah, I would say it would be incredibly difficult. I think in comparison, the environment as you go deeper into the center of the earth is much more harsh than what you would find, for the most part, for space travel, with the temperatures and the pressures you'd find.
It's actually a much more hostile environment than going in space or down in the ocean. And in particular, the high pressures are such that we wouldn't know how to make a vessel that you could go inside and not get crushed down, really past a few miles. The pressures would start to get too high for any sort of normal technology.
We have ignition sequence start.
We already know a thing or two about building complex vehicles. Could we spin off space technology to help get us to the center of the Earth?
Clearly, one of the biggest issues you're going to have with a trip like that is going to be the extreme temperatures and pressures. Some of the best materials that we have currently for dealing with temperatures like that would be the ceramic tiles in the shuttle, or some kind of carbon-carbon, or any type of carbon-based material.
But here's the hitch. While man-made materials like ceramics and carbons withstand heat, they lack strength. Metal is strong, but most steel melts at around 2,500 degrees. The temperature at the Earth's core is probably 14,000. We need new materials to build our capsule, or to shield it.
Sometimes, if time is on your side and you're not going to be exposed to the temperature for very long, simply having a material with enough heat capacity to absorb the heat that's flowing into the system without melting would be sufficient. The best bet that I know of as far as temperature is diamond. And even diamond, I think, has a melting temperature of 3,200 Kelvin. So from a material standpoint, I don't know of any materials on their own that would be able to withstand those temperatures.
As well as being the ultimate adornment, diamond is the hardest substance known. We can manufacture diamonds, But could we make one big enough from which to build a capsule?
Well, the diamond certainly would be the strongest material and would allow you to have the highest pressures. It's not entirely clear you, of course, can fabricate an entire vessel.
A tunneling machine using conventional technology would be destroyed by heat and pressure long before it reached the Earth's center. Only 20 miles into its 4,000-mile journey, it would melt. But if one day we could conquer these technical problems, there may be a way we could send a capsule deep into the planet. We'd have to harness the most powerful force on Earth, continental drift. The theory of continental drift, also called plate tectonics, was finally accepted by science in the 1960s, a century after Jules Verne's day. It said that the land masses we're familiar with started out as one supercontinent. This sat on plates that migrated across the globe. But the plates haven't stopped. In another 20 million years, our world will look very different. This is the San Andreas Fault. These two plates are sliding past each other. At the same speed your fingernails grow. Most of the time, these plates slide smoothly, but occasionally they get stuck. And this causes earthquakes. Plates don't always slide past each other. In some places, one plate is forced beneath the other. That's what's happening underneath Japan. It looks serene, but beneath the surface, it's a different story. The Pacific Plate and Asia are colliding head-on. Below the picturesque landscape, the Pacific Plate is being driven under Asia, a process called subduction. It makes Japan a hotspot, not just for volcanoes, but for earthquakes as well. Japan's volcanoes look genteel, but don't believe it. It's feared they'll destroy the islands they once created. If we could take our capsule deep below Japan, we'd find that the volcanoes aren't like the ones we saw in Hawaii. At Kilauea, the heat and pressure of the deep earth blast out streams and fountains of molten lava. Under Japan, there's a different driving force beneath volcanoes, subduction. As subduction buckles and breaks the Earth's crust, seawater flows in. Hot rock and cold water are an explosive mixture. Subduction triggers earthquakes too. Tetsuro Orabe is a professor at the University of Tokyo. 8 years ago, a quake killed 6,000 people, including his mother. He now works on earthquake prediction.
Japanese island arc locates on the western rim of the Eurasian continent, where the plate of Pacific Ocean floor goes down beneath the island arc. So that kind of active setting makes all those natural disasters like a volcanic eruption and earthquake. In 1995, there was a Kobe earthquake which killed about 6,000 people. But it was not predicted, and all the seismological method failed to predict the earthquake.
To predict earthquakes better, we have to know more about their causes. A capsule designed to travel to the center of the Earth could help. If we weren't in a hurry, we could bury it in the Pacific Plate and wait for a few million years. It would end up under Japan, courtesy of continental drift and subduction. The rock we parked the capsule in is solid, but also moving.
And this is what the mantle does. It flows very, very slowly at about a centimetre or so a year. But like glass, if you hit it with a hammer, it breaks.
And that's what causes an earthquake. 150 miles down, one plate tries to move against another. Incredible pressure builds until one slab breaks and slips. Because of its unstable foundations, Japan has one of the most comprehensive networks of earthquake sensors in the world. 1,700 underground sensors listen out for a hint of movement in the crust and mantle. The data is beamed back to a national monitoring center that records every tiny moan and groan. Every quake, however small, is mapped in 3 dimensions. The quest is to find a pattern that will predict future quakes, because Japan is due another big one. It's expected here, Tokyo. Tokyo has a population of over 12 million. Every 200 years, this area is hit by a huge earthquake. The city is built over a busy intersection where 4 of the Earth's plates meet. The subterranean collisions never stop. That's why Japan's so prone to earthquakes, and why it's so hard to see them coming. It's a high-stakes game. Millions could be hurt or killed. To get better data, they will have to drill down into the colliding plates, more than 6 miles.
JADGE stands for Japanese Ultra-Deep Drilling and Geoscientific Experiment. That is to drill about 10-kilometer hole down to the subduction zone.
They've chosen a site, but what about the technology?
The target area of the JADGE project is very active, and probably the temperature could be more than 300 degrees at the depths of 10 kilometers. And then the 300 degrees makes every operation of the drilling very difficult.
And that's the same for our capsule. We'd need more technology for it to survive the intense temperature and pressure. What will the capsule find at the center of the Earth? A mammoth nuclear reactor? On its way to the center of the Earth, our capsule will have to navigate a sea of molten iron. Surging around the inner core, this generates magnetic energy. Just 1% of it escapes from Earth, but that's enough to form a protective shield 37,000 miles out into space. But how is so much energy produced? As Jeremy Bloxham admits, we're still struggling to find out.
Really, the burning question which we all wish to address through our investigations of the Earth's magnetic field is, how is the field generated? What is the mechanism that gives rise to a field which has persisted for at least 2 billion years?
One geophysicist has a radical suggestion. Marvin Herndon speculates that at the center of the Earth, we may find a natural nuclear reactor.
One of the problems that has existed in science is figuring out what is the energy source that drives the Earth's magnetic field.
He doubts that it's just a ball of iron that's been cooling for 4.5 billion years. There's simply so much power. Enough to maintain the magnetic shield, move continents, and make volcanoes and earthquakes. Herndon suspects there's something much more powerful down there.
One of the implications that I suggested early on was the possibility that the changes that we observe in the geomagnetic field may have their origins in changes in the output power of the nuclear reactor.
Could this explain the drastic changes our planet has gone through? Like the extinction of the dinosaurs? Could the melting of the ice caps have been caused by a surge of heat from a nuclear core? Because unlike an iron core, a nuclear one can fluctuate.
A nuclear reactor can shut itself down and start itself up again. Its output can vary, or it can remain very constant.
Herndon's ideas are controversial. Few agree with his theory, and the debate continues. But one thing isn't disputed. The magnetic field is changing, and measurements show it's been doing so for some time.
Based on the results in our current systems that are sort of basketball size, then we have this plan for a much larger system that would be 10-foot in diameter sphere filled with liquid sodium, so about 15 tons of the metal. But it would be driven the same way as the existing experiments, but then at parameters that are much closer to the parameters thought to exist in the interior of the Earth.
The capsule we built to journey to the center of the Earth is under its own power after hitching a ride in the rock. Now, sensors show the going is about to get tough. "1,800 miles down, the capsule nears the boundary between the mantle and the outer core. The huge temperature here melts away the remains of the tectonic plate surrounding the capsule. Now, the capsule must be released from its protection and power itself. The capsule drives forward through the liquid outer core. Now, it must cut its way into the solid inner core. It's solid because there's massive pressure here, 4 million times greater than at the surface. And 1 billion amps of electricity surges between the cores. This, at last, is our journey's end, the center of the Earth. The only place on our planet with no gravity. Jules Verne's influence on the world has been immense. He propelled generations of young readers toward careers in science, engineering, and exploration. He inspired the inventors of the helicopter, the submarine, and the radio. There's little doubt that his novels influenced the minds that have changed our world. Little did anyone know, when Jules Verne died at the dawn of the 20th century, that he would have such an effect on the future. His life is summed up in the inscription on his tomb: "Onward to immortality and eternal youth." If Jules Verne was right, maybe one day we will be able to journey to the center of the Earth.